Hello, I am here to present you the results of our SBIR Phase 2 program, Low Swap Laser System for Quantum Inertial Sensors. This program responds to SBIR solicitation N68335-23-C-0169, Compact Phase Locked Laser System for Atom Interferometric Inertial Sensors. First, I want to say a few words about our company. Physical Sciences, Inc. is a 50-year-old company, employing more than 250 employees. We are a high-tech company with broad expertise that includes underwater sensors, integrated photonics, and optical communication. Physical Sciences, Inc. is dedicated to transitioning technology from academic research to applications and successfully demonstrated bringing new technologies from the university's lab to real-life applications. We perform applied R&D for industrial customers and all agencies of the U.S. government with a focus on hardware solutions. Its product areas include ISR systems, laser-based sensors, radiation sensors, RF and optical components, and tactical systems. For every dollar of Phase 2 SBIR investment, Physical Sciences has secured nearly 3 times that amount in Phase 3 funding. Before describing the low swap laser system for quantum inertial sensors, I would like to present other developments of quantum sensors and their components that we are working on. Recently, we have successfully demonstrated a 3D printed ultra-vacuum chamber suitable for quantum sensors. Such vacuum chamber provides lower swap than traditional stainless steel ultra-high vacuum chambers. Further, 3D printing allows additional flexibility, fast prototyping, and geometries that are not possible relying on traditional manufacturing. We designed and manufactured 3D printed vacuum chambers that are able to maintain pressure below 10 to 9 torr and are suitable for quantum sensors. Physical Sciences is developing an atomic beam source that is contained within a microfabricated vapor cell. The atomic beam of cesium atoms can be further used for quantum accelerometers or gyroscopes. We have successfully demonstrated a compact heading error-free scalar magnetometer. Recently, we started working on an ultra-fast high extinction ratio optical switch based on frustrated total internal reflection. High extinction ratio optical switches, also known as optical shutters, usually have a mechanical or electro-optical nature. Mechanical shutters have an impressive extinction ratio, but they are bulky and relatively slow with a switch time order of 1 millisecond. Electro-optical switches based on acoustic or electric optical modulators are much faster and can be made very small, but they have a limited extinction ratio. The developed ultra-fast high extinction ratio optical switch combines the advantages of mechanical shutters and electro-optical switches. Furthermore, Physical Sciences has developed a source passively regulated alkali atom source. Accurate navigation is crucial for military missions because it ensures precise targeting and coordination among multiple units. While GPS provides positioning, navigation, and timing so-called PNT services, there are multiple areas where the GPS signal is not accessible. For example, canyons, underground or underwater, urban environment, etc. Further, the GPS signal can be spoofed by a counterfeit radio signal, which is even more dangerous. For these purposes, an inertial navigation system is created. In particular, the pendulous integrating gyroscopic accelerometer, which is pictured on the right, may be an alternative. However, such systems suffer from complex assembly and are subject to wear and tear typical for mechanical systems, which degrades their performance over time. Accelerometers based on atom interferometers have significant advantages. Inertial sensing. Based on atom interferometry readily provides strategic-grade inertial measurement performance for navigation. Further, inertial sensing based on atom interferometry relies on fundamental properties of atoms that don't change with time and are not subject to wear and tear. or time drift. However, currently, atom interferometers require complex optical systems. In particular, optical systems are a significant part of the swap of quantum inertial sensors. In the pictures below, we present a present implementation of such atom interferometers. Overall, swap and ruggedization of current quantum inertial sensors is a major obstacle for using for navigation. Physical Sciences, Inc. developed a simplified atom interferometer laser system, in short, SAILS module. Our key innovation is the recognition that only two frequencies are required at any given time in the sequence, and the development of a universal atom interferometer laser system using a reference laser, commonly referred to as a master laser, combined with two frequency agile lasers, commonly referred as slave lasers, in a low swap package. The key features of the SAILS are single-feature laser spectroscopy and auto-locking circuitry, cascaded laser lock architecture with 3 photodiode distributed Bragg reflector lasers at 780 nanometers, master laser that is referenced to rubidium transition via modulation transfer spectroscopy, slave laser that is offset frequency locked to master laser at 1 to 5 gigahertz, subslave laser, which is offset phase locked to slave laser at 1 to 7 gigahertz, and available small form factor components. Overall, this development results in generating all required optical frequencies for a pulsed atom interferometer system, as well as offering a low swap and high level of ruggedization. Here we briefly describe the current status of the developed laser system. Please note that since preparation of this presentation, a significant progress was made in the lab. We have demonstrated a benchtop setup that has needed performance in terms of phase stability, locking range, frequency switch time, and frequency stability. We have designed the prototype system relying on best practices for ruggedized lasers, able to withstand high vibration and thermal stress environments, picture below on the left. Laser housing has been machined, picture below on the right. Recently, we have populated the housing shown on the picture with all needed optical components and aligned laser beams. Saturated spectroscopy of rubidium-85 has been demonstrated. Below, we list the key features of the SAILS setup. 1. 3 cascaded laser locks in master, slave, and subslave architecture. 2. 2 spatially separated fiber-coupled outputs for atom interferometer transitions, namely 2-photon Raman, and atom preparation and detection, including atom cooling and trapping. 3. High-power narrow line-width distributed feedback lasers in hermetic packaging at 780 nanometers. 4. Fast startup and auto-locking for all lasers. 5. High extinction optical isolation. 6. High extinction compact optical shutters. 7. Frequency agile frequency hopping. 8. Phase coherent slave and subslave lasers with crossed linear polarizations ideal for ALS. 9. Magnetic shielded rubidium vapor cell reference. 10. Universal compatibility with atom interferometer architectures for strategic grade inertial navigation. And, finally, low swap and high level of ruggedization. On this slide, we discuss the current program's key performance parameters that are relevant for the transition to fleet. The key performance parameters are shown in the table below. We would like to emphasize a few numbers. The optical power produced of 50 megawatts is sufficient for laser cooling and trapping more than 10 million rubidium atoms. The locking range of 1 to 5 gigahertz is sufficient for covering all frequencies needed for a rubidium-based atom interferometer. The demonstrated phase stability is sufficient for navigation grade equivalency, or better, depending on specific parameters of the atom interferometer. The frequency stability is sufficient for both efficient laser cooling and interferent pulses. The most important volume and energy consumption are orders of magnitudes below present atom interferometer laser setups. Below, we present basic market analysis. This is still an early R&D effort. There is currently no established market in the industry for such technology, because overall atom interferometers based on laser-cooled atoms are still in the R&D phase. This technology requires additional phases of development prior to implementation for prototype quantum sensors. The technology is of interest to multiple Department of Defense agencies. The initial champion for the technology was Strategic System Programs, but also of interest to other agencies, including Office of Navy Research, Naval Research Lab, Air Force Research Lab, Space Force, and interest of multiple DoD prime contractors such as Draper, Honeywell, Northrop Grumman, and Lockheed Martin. Finally, the technology is broadly employable beyond the Department of Defense's needs. Technology can be potentially used for non-DoD related government agencies and industries, such as NASA, DOE, and the aerospace industry. Listed on this slide is the address and phone number of Physical Sciences. Further, please find the contact information of Business Point of Contact Joel Hensley, Vice President of Physical Sciences, and the Technical Point of Contact Vladislav Ivanov, who is the Principal Research Scientist and Principal Investigator of this program. Feel free to contact us with questions and inquiries about sales. I would like to remind you that Physical Sciences, Inc. offers a low swap, high-performance components for atom-based quantum sensors. Thank you for your time.